Hi, Wade Hampton students. Welcome to the first lesson in Unit 2A on covalent bonding. So we're going to talk a little bit about different kinds of bonding in this unit. And in this very first lesson, we're going to teach you how to classify bonds into different types and also examine something called the polarity of bonds. So, first of all, if we're going to be talking about bonds between atoms, what's a bond? Well, basically, it's just a force that holds a couple of atoms together. And the way that they work, pretty much all different kinds of bonds work, is off the same basic premise, and that is opposite charges attract. So, a positive charge and a negative charge attracts. Now, we know atoms have both things, right? The middle of the atom is positive because you've got all your protons in there, and the outside of the atom is negative. And so when you get a couple of atoms together, you get some interesting interactions here. So there's some repulsive forces between the two nuclei, and there are attractive forces from the electrons of one atom to the nucleus of the other. And if that balance between attractions and repulsions gets just right, and those atoms can find a good distance from one another, then the two atoms can form a bond. Okay. All right, so there's two basic types of bonds. There are covalent bonds, and then there's ionic bonds. And the principal difference between those is that in covalent bonds, we've got electrons being shared. And in ionic bonds, we've got electrons being transferred or moved from one atom to the other. Okay? So here's a simple case of a couple of hydrogens. These two hydrogens, when they're by themselves, each would have one electron. But when you get them together, each hydrogen shares its electron with the other, so both electrons spend some time in the middle between atoms. And since both of these nuclei are both tugging on this single pair of electrons, that creates a bond. And a lot of times you can show that in some of the models that we're going to be making with just a simple dash. So this dash represents two electrons in here in a covalent bond. Now in ionic bonds, electrons are moved from one to the other. This model here shows basically a sodium with only one valence electron. This is a Lewis dot, so it's just showing a valence electron. And then this chlorine has 7 valence electrons. And so remember, chlorine would love to gain one to have the same number as the noble gas argon. Sodium would love to lose one to have the same number of electrons as the noble gas neon. And, once those two kind of give up their electrons, then you end up in a scenario where sodium has a positive 1 charge and chlorine has a negative 1 charge as an ion after that move happens, and the two kind of stick to each other. Okay, so when is sharing going to happen versus when is electron transferring going to happen? Well, that basically depends on how much the two atoms can pull on electrons. And if you remember back from the last unit, how well atoms pull on electrons is something called electronegativity. Okay, so electronegativity, okay, remember this is how well atoms pull electrons, okay? So we're going to kind of break this down into 3 categories, I guess. If the two atoms don't have any difference, there's 0 difference, then you're going to end up in a situation where the bond is nonpolar covalent. In other words, the two atoms pull on electrons exactly equally. Covalent basically means that we're sharing the electrons instead of just moving them from one atom to the other. Now, if you have an intermediate difference, this means medium-sized difference, then you can end up with a polar covalent bond. And if you have a large difference in electronegativity, then if it's big enough, one atom pulls so much stronger than the other, then you can end up with an ionic bond. Now, there is actually a scale of electronegativities that goes from all the way down here below 1 to electronegativities that are all the way up here at 4 for fluorine. That's the biggest electronegativity in the table. And you'll notice that, the noble gases aren't here because they don't tend to bond, and so it's tough to measure how well they pull on electrons. And you can subtract to kind of determine how polar a bond will be. You know, if you're bonding boron to carbon, you can take a look. Oh, the difference is 0.5 in electronegativity, and you can classify bonds that way. We are going to do that a little bit of a different way. Instead, we are going to basically just look at the kind of bonding in three categories based on the kinds of elements that are inside them. So you'll notice the metals have really low electronegativities and the nonmetals have really high electronegativities. So anytime you've got a metal and a nonmetal, we're going to say that the bond type is ionic. Okay, that's the biggest difference. Okay. If you end up with two different nonmetals, then we're going to say that it's polar covalent. And if you end up with a metal and a nonmetal, I'm sorry, two of the same nonmetal, then we're going to say that it's just nonpolar covalent. Okay, so here's some examples of each type. Suppose I had like a bond between sodium and oxygen. Okay, if I had a bond between sodium and oxygen, sodium is a metal and oxygen is a nonmetal. This is going to be an ionic bond right here. If I had a bond between, say, phosphorus and oxygen, those are two nonmetals, but they're two different nonmetals. This bond would be a polar covalent bond. And if I had a bond between oxygen and oxygen, then the two atoms have exactly the same electronegativity. Neither atom pulls on the electrons any better than the other one. We would say this is a nonpolar covalent bond. Okay? So basically, are they metal and nonmetal? Are they two different nonmetals? Are they the same nonmetal? It's pretty easy to put them into one of those three categories fairly easily. It's probably a little bit more accurate to use differences in electronegativities, and there's some range of values there that you can kind of go by. But for our purposes in this class, we're going to just limit that to, hey, what kind of atoms are we connecting together? Metals, nonmetals, different ones, the same one, that kind of stuff. Okay? All right, so a dipole moment is the direction of polarity, okay? And the gist with a dipole moment is that, say you had a chlorine and a hydrogen here. One of these atoms pulls on electrons a little bit better than the other. Actually, in this case, chlorine pulls quite a bit better than hydrogen, but technically they're still both nonmetals. And so, the electrons get pulled closer to the chlorine, and the effect of that is that this side of the bond, where the electrons spend the most time, ends up partially negative. And that's what this little squiggly kind of S that meets back up here, this is just a Greek letter. I think it's an uppercase sigma, but that just means a partial negative charge. Now, this is not quite as big as like a -1 charge, but it's still pretty big, okay? Now, you can show those or predict which side is going to be partially positive and partially negative in bonds like this, basically just because the negative side is going to have a higher electronegativity. Okay, and if you remember from, Ram and Rhine stuff, if we're saying Ram's down here and Rhine's up here on the periodic table, the E for electronegativity gets bigger as we go this way. Chlorine's way over here and hydrogen's way over here on the periodic table, and so chlorine can definitely pull better than hydrogen, okay? This picture is supposed to represent a nonpolar covalent bond. And the blue area is just like, where the electrons are spending time, and so we're saying the electrons are spending time equally around both atoms, and so this is equal sharing. Here we have unequal sharing in the hydrogen-chlorine example. And so that would be a polar covalent bond. But it's still covalent because we're still sharing. Now in the kind of, sodium and oxygen or bond or sodium and chlorine bond or something like that, where you have a metal and a nonmetal, if the electrons actually get moved from one atom to the other, then you're going to end up in an ionic scenario. So basically, the electrons are not spending any time between the two atoms. It's just you would view, since this atom has lost an electron, the whole atom as a whole has become a positive ion. This has become a negative ion, and then you kind of, instead of looking at the parts of the atoms, you just look at, hey, these two atoms are oppositely charged, and so the whole atoms tend to stick together. So now, diatomic molecules, this means two atoms, by the way, diatomic. These things are going to be polar anytime you have two different atoms. And because, if you got two different atoms, then they're going to be pulling on electrons differently. They're going to be nonpolar pretty much only in the case where you have the same atom bonded to the same atom, okay? Same equals nonpolar. Now, if you get a polyatomic compound, this gets a little bit more complicated. I'm not going to spend too much time on that right now because we'll come back to it in a later lesson. Okay. Now, there's a couple of things that you can do to show bond polarity. We already showed you kind of this partial positive and partial negative, and you can just kind of write this on either side of a bond. If you were just writing this in regular text, you might say, all right, I got HF, and this side has the partial positive. Typically, it's put in parentheses, kind of like that. This side has the partial negative. And again, it's not always going to be on the right side for the negative. It's, whichever side has the higher electronegativity. Fluorine has the higher electronegativity here. Another way to show a dipole moment or show the polarity of a bond is with an arrow. And you'll notice this is kind of a special arrow because the arrows kind of have a plus sign on the end of them. So, and that makes sense because the plus sign is on the same side as the partially positive low electronegativity element. So we call this a dipole moment vector or a dipole moment arrow. And the gist is, it's just showing which way the electrons are getting pulled, okay? So here's an example of a carbon dioxide molecule. We've got carbon connected to oxygen here. And if you compare the electronegativity of these two, oxygen's got a slightly higher electronegativity than carbon, actually quite a bit higher than carbon. And so the electrons that are in this double bond get pulled closer to the oxygen than they do to the carbon. And so the dipole moment arrow shows those electrons getting pulled. Okay, I don't really want to look at the whole molecule right here, but let's just zoom in on just this part of this connection. So suppose you had a carbon to oxygen bond. Now, if I had a carbon to nitrogen bond, and this might happen to be a triple bond if this thing were maybe a cyanide, but the gist here is that, if you look at the electronegativity difference between C and O, they're farther apart on the periodic table, which means that the difference will be bigger. They're more polar. And if you look at the electronegativity difference between C and N, they're closer together on the electronegativity difference trend. And so since they're closer together, it'll still be polar, but it's not going to be as polar. And so kind of an important thing to show here is if you were using dipole moment arrows like this to compare this bond and this bond might have a smaller vector or a smaller dipole moment arrow just to show that that bond, the electrons in that bond are not getting pulled as hard to one side of the bond than the other. Okay, so if I had to say, if I've got C connected to O versus N connected to C, which one of those is more polar? I'm going to have to say that one is more polar because it's farther apart in electronegativity difference. Okay? All right, so that, my friends, is bond type and polarity. Just a quick little review here. Again, probably the most important things are can you tell what kind of bond it is by the same nonmetal, two different nonmetals, or a metal and a nonmetal to put it into one of those three categories. And then how can you tell which side of the bond is positive and negative? The negative side has the higher electronegativity. If you're comparing bond polarities, the more polar bond is going to be the one where the two atoms are farther apart on the electronegativity trend. All right, until next time.